So, vanakkam. So, we will continue one lecture on engineering seismology. So, last class we have been discussing about the interpretation of the earthquake record. So, particularly, how we can get a time domain parameters. So, we have been started noting down the peak values, which is basically the each component of the record will have the acceleration, velocity and displacement. So, you can get integration and differentiation to get one recorded data, the another two are the basically derived by integration or differentiation. So, we have seen that basically the each seismic station will have the three component of the record, and each component of the record can be converted into three form such as acceleration times t, velocity times t, displacement times t. So, in the each record we will have like the acceleration peak values, okay, so which is called as a peak ground acceleration or peak horizontal acceleration. Similarly, the velocity form the peak values are peak horizontal velocity or peak ground velocity. Similarly, the displacement, so the peak horizontal displacement or peak ground displacement values. So, these values we have seen that the accelerations are very sensitive to the high frequency range, velocities are intermediate frequency range, displacement are the low frequency range. So, in general the accelerations are predominantly used for the design of structures since it is related to the inertial force calculation. So, the velocities are used for the tall structures and the intermediate frequency range of structures is being used. Displacement has actually a lot of issue with the noise and it is very difficult to get a proper displacement plot. Okay, but now because of the digitalization it is maybe possible, but generally the displacement based approach structural design they use a displacement times t. So, we have also seen that this peak value sometime very high when compared to the other amplitude in the same record or sometime slightly higher than the other record. So, in that case, so considering one peak may not be sufficient. So, then there is a effective acceleration, okay, so those kind of terms also we have seen. So, then we have seen that this amplitude, okay, how many times it repeats depends on that the damage of the structure is defined, particularly poor pressure generation, landslide, liquefaction related phenomena. So, the scientists start using the basically the duration of the record, that is like how many, so the strength of the record, how much it is basically amplitude is repeating per a given period. So, we have been start seeing at the, so the effective duration, significant duration, so things like that. So, which is basically relate a amplitude and the energy released by the earthquake, how that energy, how much time duration it released or it is impact the structure. So, based on that we have seen. We also discussed that the arrival time picking up for the P and S wave will help you to identify basically the your epicentral location of the earthquake if you have the 3 station, and if you have 3 and more station you can also get a the hypocentral or focus point, the depth of the earthquake in that. So, today we will be starting again with the epicenter things kind of things. So, for the given earthquake, if it is recorded at 3 places, at least need to precisely identify a earthquake. How these 3 place stations are, your P and S wave changes with the distance, that is what we are going to see. So, if you look at this picture, so if you look at this picture very carefully, you can see that, so this is basically the earthquake record, okay. So, recorded at a different place. This is basically a distance in the kilometer, you can see this is the distance in the kilometer. So, the distance in kilometer, so this is basically the origin of the earthquake. So, this is actually the time after the earthquake minute. You can see that this is like a TEIG, okay. So, is one of the station in Mexico, the another one is SOCO, the another station, so another the SSPA is another station. So, you can see that this station records a P wave arrival, since this station is very close, roughly about 800 kilometer from this one. So, the first P wave, then the S wave arrival is there, you can also see the amplitude, and then the next station is close to 1800 kilometer from the epicenter, you can see the amplitude. Okay, then the S wave arrival time. So, then again the another station was around close to 3300 kilometer away, you can see the again S wave and the P wave arrival time. You can see that this S wave arrival time you can peak, and then the arrival time of this point basically. So, this one. So, basically this portion, so this portion and this portion and this portion and this portion and this portion will give you the arrival time. So, you get the amplitude from here, you can see. So, the amplitude from here. Okay. So, this is the peak amplitude. So, I mean the peak, marking peak actually. So, if you look at this very carefully, so if you look at this very carefully, so this is the peak point. So, here basically this will be the peak point, here this will be the peak point. If you look at that with the distance, okay, so the arrival time is keep increasing, okay, that is the one information we can get. Second, the amplitude, okay, so the P and S wave, generally the P wave we do not consider as a amplitude required for the peak ground and velocity or displacement part, only the S wave part we consider. So, generally the P wave will be lower than the S wave amplitude. So, you can see here this amplitude, this amplitude, this amplitude, you can see these values of the amplitude also keep changing. Second, you can also look at the component of the like how much time the S waves are repeating, okay. So, that also you can see. So, you can see here basically. So, this is repeated up to this, here you can see it is repeated slightly larger. So, here you can see it is repeated up to this. So, your duration, okay, then the amplitude keep increasing with the distance. So, that is the one observation we can make from here, and then the gap between the P and S wave arrival time, basically this here 1.5 minutes, 3 minutes and 5 minutes. So, this time also keep increasing. So, these details are useful basically to show how the where the exactly the origin of the earthquake basically located, okay. So, as we have know that the P waves are faster waves which arrives first part, and the second the S wave which arrives later part. The S and P wave time determine how far the seismic wave have travelled from the seismic station. So, the delay between the P and S wave arrivals on seismogram are matched to the curve to find out a distance of seismic station from the source to seismic waves. So, basically this particular plot has been taken from the website given here basically. So, this is the website which has been taken. So, you can also verify that this website details for more information kind of things. So, you can see the plot of the this distance. So, basically, so from the origin, so 900 kilometer, the another one was 1800, 300. So, basically these are all the locations, your stations, okay. So, by plotting all this curve, basically you have located the place where this meets, like last we have discussed last class, no. So, where it meets basically. So, this part basically is here your epicenter location or earthquake location, okay. This is what you are. So, this is a way we will locate a earthquake. Last class I drawn in the freehand and explained that. So, this class I shown you that how the waveform is differ. So, if you have to find out a epicenter, so you need a 3 record and you have to pick up P wave and arrival very clearly from that, like here what we have given. Then the time travel will be taken and then you can know. So, in the physical cases, if you know basically here you are using that time of arrival and velocity in the region to estimate a distance, okay. So, in the physically that velocity in the region like P wave velocity, S wave velocity, we are given shown the range, you know. So, generally what in the region if you have the data recorded from like this for the known distance, then you can actually estimate what is the average P wave velocity you can use, average S wave velocity you can use for this kind of calculation. For example, so this station and this station, these stations are far. So, this in between this velocity will be different, okay. So, this will be the like your Vp and Vs. Similarly, so this velocity may be different, it no need to be necessarily the same, this you have to find out. Similarly, so this velocity will be different as the geological terrain varies, the wave characters are function of the stiffness density of the geological material, like P wave is the function of the constraint modulus, S wave is the function of the so the polar moment of inertia, and then basically the shear modulus of the property. So that varies, then this values also varies. Okay, so if it is, you can find out what is the average value by getting lot of this kind of measurement at a particular place, or doing the deep geophysical surveys on those location. So this particular graph also available in the this website shown here. So you can, if you want more information, you can refer the same. Okay. So this is the direct wave where we can expect basically the PGA and PGV and PGD, okay, and then a duration which we have seen here. This is the part where duration, so depends upon the type of duration, your threshold value keep changing, but this is the data we will be predominantly using to arrive the duration part. So these details, okay, will be help you to identify the infer from the earthquake data, which is useful for the engineering so application. So the another form of data, so whatever we discussed, which is directly the time domain parameters, okay, where you just look at a acceleration time history of the data, and you will take that data basically to get a direct observation from the acceleration, velocity, displacement, as well as the duration part. So this data basically you can convert, okay, so in the frequency domain, okay, then you can interpret a parameters which is useful for the simulation as well as the structural analysis. Okay. So that kind of interpretation is a frequency domain, so characteristics analysis of the frequency domain analysis. So we will see what are those parameters, how we can interpret in the so this one. So as we have shown that this is the typically one component where the acceleration and then the time record. So you can also see that these records are basically, so this is actually the extracted portion of the entire record. You can see that this record basically dominated at this place. So predominantly these data are basically, this is the P wave, okay. So this is the, so maybe the somewhere here the S wave will be there. So if you zoom in, then you can see that the strength of the earthquake lies between somewhere here. So these portions are more impact energy to the structure. So understanding of this we need to deal in the very properly and so systematic manner. So that is what we do in the frequency domain analysis and estimate the frequency domain parameters. So the earthquake produces complicated loading with the component of the motion that span broad range of frequencies. Only the simplest analysis are required to show the dynamic response of the complained objective by the building or bridges or slopes or soil deposit very sensitive to the frequency at which they are loaded. So basically the different structures has its own natural frequency. So the earthquake frequency and natural frequencies are very close, then you will get the response is very big and it will be, may also get a resonance. Okay. So in that case, so depends upon the building what we design, its natural frequency, you need to identify what frequency range of the data you will be interested for using the analysis. So in that context only the frequency content describe how the amplitude of the ground motion distributed among different frequencies. So earlier whatever we have seen, basically the amplitude distributed over a time, okay. But here we are basically looking at how the amplitude of the ground motion distributed among different frequencies. Depends upon the your frequency of the structures, what amplitude you need to consider for the design, you will be taking from this frequency domain characteristics. Since the frequency content of the earthquake motion will strongly influence the effect of that motion, characterization of the motion cannot be complete without considering the frequency of the content. So only using the time domain parameters may not be always good, okay, to get analysis. So you should look at that how the frequency the amplitude of the frequency content varies. The frequency domain parameters are basically the Fourier amplitude, phase spectrum, power spectrum. Several definitions of the response spectrum are used in the quantification of the strong motion. The 5 type of response spectrum used are relative displacement, relative velocity, relative absolute acceleration, pseudo velocity and pseudo relative acceleration. So these are all the terms and described in the frequency domain. So we will be discussing the important terms which you will encounter in engineering application of these kind of things. So first we will discuss about the response spectrum. So, the response spectrum, the spectrum is basically a plot of frequency versus okay, so a amplitude, okay, that is the spectrum, or the frequency also can be plotted as a the natural frequency or natural period by making a inverse. Okay. So, this is it's itself written as spectrum the response. So, it is basically the response of something plotted as a spectrum is called as a response spectrum. So, it is used extensively in the earthquake engineering practice. The response spectrum describe the maximum response of the single degree of freedom system to a particular input motion as a function of natural frequency like a natural period and damping ratio of the single freedom system. So, basically the spectrums describe the maximum response of the single freedom system to a particular input motion as a function of natural frequency or natural period and the damping ratio in of the single freedom structure. So, here it is basically clear that it is a response of a single degree freedom system. So, basically a single degree freedom system is generally assumed as a, so the a single pendulum with mass. Okay. This is a single degree freedom system. So, the damping and other things you can incorporate, this is the simplest form you can assume. So, this response, okay, maximum response of this for a given input by changing its natural period. Okay. So, the response, okay. So, then this height will decide the your frequency and you will give a typical input and then you measure a response. So, that response only is called as a response spectrum. So, the frequency content of the two motions are reflected in the response spectrum. The rock motion produced higher spectral acceleration at a low period. So, then the did a soil motion lower spectral acceleration at a high period. So, this is the sum of the observation. The higher long period content of the soil motion produced spectral velocity and displacement much higher than those of the rock motions. So, what are the cases how these amplifications are different is actually is described in the statements actually. So, if you look at that, as I told you that, so you take a single degree freedom structure and take a some input motion. So, okay, then you start vibrating. So, this will you will get basically the response of this, okay, which varies with the time based on this. Okay. So, the response first you give, so it will respond, then it will keep on responding, then you can see that there is a point where you get a maximum response. So, that point is noted down. So, now you know what is your period of this structure which you are estimated for that period for this given motion what is the response. Similarly, now you change a period of the structure by varying a height, okay. Then again same input you measure a response, that response is this one which is plotted. So, similarly you change, you will keep on altering that. So, where the period is changes from like for example 1 second natural period or natural frequency whatever you want. So, 1 second, 2 second, 3 second like that or 1.5, 2.5 like that you keep changing your the height to vary the period and the same input you try to observe a maximum response. That response basically plotted as a the time. This time is actually this is actually period. Okay. So, this period is actually your structural period of the natural period of the structure. Then you so in the 0 period you will get some acceleration. So, 0 period, so you will get some response. Okay. So, then the 1, 2, 3, 4, 5 like this. So, this connecting of this is basically a response spectrum. Okay. So, this will be the spectral acceleration because you get a response. So, this is the response spectral acceleration or response spectral velocity. So, this will be your period basically. This is the natural period of the system or structure where you will be using the. So, this is done for the single freedom system, so that the multi freedom system you can take it as a with multiple level of multiplication of the level. Okay. So, this is basically a period. So, this is the period in second or frequency in hertz. Okay. Then we will keep. So, here you can observe that this is actually a 0 period. Okay. The period equal to here equal to 0, correct. So, then this keep changes up to the So where the response plotted kind of things. So this acceleration, okay, is called as a zero spectral acceleration. So if you look at this acceleration, this is the maximum response. So that means if the zero so period, the structure basically zero natural frequency means 0. So basically your peak acceleration of the input, okay, the peak ground acceleration equal to the 0 spectral acceleration. Why? Because at 0 period there is no structure, so your input motion is the your response. Okay. So then when you have a period, this response changes, that response only plotted here. So this kind of analysis, okay, basically the response spectrum analysis, okay. So this involves solving up mathematical equation for the single degree freedom system. So this is basically, you can see how the response of the you will get like this. So since this course, as I told you, that it is also taken by the +2 level or degree course people with geology or geophysics. So we are not going very detailed in the response spectrum analysis. Generally this response spectrum analysis is taught in the structural dynamics. People who study about the structural dynamics in BTech or MTech course, so they know about what is the response spectrum. So that like single degree freedom structure response for the given input at a different natural frequency and with the known damping level. Okay. So generally the 5% damping is generally used. So if you have the higher damping level also, you can do for the different damping level and get a curve. So this curve is basically a function of your natural period and damping. Okay. So the single degree freedom structure. So when you are going for the multi degree, so this response can be extrapolated and modified for the design. So this kind of spectrum given in the code, okay, the response spectrum is used get from the several input motion and try to accumulate that and then try to process in the smoothed manner and get a finally the design spectrum or normalized spectrum that is given in the code for the design of structures. Okay. So that basis for the design of structures what you are getting is basically a response spectrum. So the response spectrum may be plotted individually to a arithmetic scale and may be combined in a tripartite plot. So okay, the tripartite plot display a spectral velocity and spectral acceleration and natural frequency on a horizontal axis and acceleration and displacement in the inclined axis. Okay. So this response spectrum, okay, so individually you can take and then you can combine with several response spectrum and try to plot in the tripartite plot, and then you will understand which part of the component comes to the velocity part, which component comes in the displacement part, which component comes in the the acceleration part. Okay. So that we can analyze. So the acceleration and the displacement axes are reversed when the spectral values are plotted against natural frequency rather than a natural period. Okay. So the shape of the typical response spectrum indicate that the peak spectral acceleration velocity displacement values are associated with the different frequencies or period. Low frequencies of the average spectral displacement nearly constant, high frequencies of average spectral acceleration is fairly constant, in between a range nearly constant for the velocity. So here you can understand that the low frequency range, okay, so basically the displacement is nearly constant. The high frequency range where the spectral accelerations are fairly constant. The intermediate frequency range basically spectral acceleration velocities are the nearly constant. So which indicate that basically if you have the plot, this is I am making as a frequency. So the high frequency component, low frequency component and then the intermediate frequency component. So I assume that my frequencies are okay. So this is the frequency I assume. So I assume that it is a 0 here and highest here. So this frequency increase here. So I just use this board to explain how the response spectrum. So this is basically your plot. So we will call the period is increasing this and the frequency is increasing here. So the frequency is 0 here and the period because it is a inverse, no. So this one will be the your spectral acceleration. So in the G or centimeter per second. Okay, the unit spectral acceleration g per meter per second square centimeter. So as we told that, okay, so the displacements are constant at so the low frequency range. So the fairly constant is basically your high frequency ranges are the acceleration. The fairly constant means, so it will be like a kind of slope. Okay. Then there is a intermediate frequency, there is a velocity constant. The displacement constant will be in this one. Okay. So this is how your response spectrum look. Okay. So basically what you will get, like this you will get. Okay. So this is what you can see in the, so if you carefully watch that, you can see that it is starting here and going, then it is coming like that and ending here. Okay. So this portion basically the constant for the displacement, the remaining is the velocity. So this place for the acceleration. So this is basically, so like this. So this we have discussed that it is a z spectral acceleration or PGA. When the 0 is your structural period, your input motion will have the same signal, that maximum input motion is the GPA. Okay. So this is basically a response spectrum. So this can be also plotted in the tripartite plot. So this is for the one ground motion. So you will be taking a large number of ground motions and try to plot all the ground motion data in the single graph. Okay. Then by after taking the mean value and smoothing, then you will get a smoothed, okay, so tripartite plot. That tripartite plot will be normalized, then you will get a spectrum called design spectrum. Okay. So which we will discuss in detail the design spectrum the later stage of the class. Right now you have to know about the response spectrum of the your this one. So because this behavior response spectrum are often divided into acceleration controlled, okay, well high frequency range, velocity controlled, so intermediate frequency range, displacement control, low frequency. So this portion comes in the tripartite plot and design spectrum development portion. You can discuss this in detail. So this is about the response spectrum. The other spectrum is actually Fourier spectrum. So since the ground motion data is array equally spaced time sample interval, the discrete Fourier transformation is used. Since the deal with the finite amount of the data, it also be implemented in the computers and a numerical algorithm. So what you do, the time history data what you get actually, you convert that into the Fourier transformation. Okay, the Fourier FFT, fast Fourier transformation, okay, or the discrete Fourier transformation DFT you can do. So once you do that, basically you get a spectrum called Fourier spectrum. Okay. So the Fourier spectrum is basically the conversion of acceleration time history data or velocity time history data to the Fourier spectrum acceleration or Fourier spectrum velocity by doing a discrete finite transformation or fast Fourier transformation you can do. Okay, discrete Fourier transformation. So here the periodic function, okay, for which the earthquake is approximately written as, so this is the one when the n is corresponding to the nth harmonic, the spectrum is the function of frequency, the spectrum shows the frequency dependent characteristics of the ground motion, the Fourier amplitude plot is the plot of the Cn versus the, so the natural frequency of the system. Fourier power spectrum is pi n is the natural frequency of the system, where is you can see where the angular and then the pi n values in the this one. So this plot will be generated, that plot is called as a Fourier spectrum. Okay. So this is the typical Fourier spectrum for the different natural frequency. Okay. So for the lowest frequency you can see that the displacements are constant, amplitude displacement amplitudes are the constant. Okay. So the higher frequency where the accelerations are constant, intermediate frequency the velocities are constant, you can get a smooth curve of this, you will see that constant kind of things. Okay. So this is how you will get a Fourier spectrum. This Fourier spectrum further will interpret get the Fourier domain characteristics of the earthquake. So we have seen that the Fourier domain characteristics, one of the response spectrum is the Fourier, the another one is the Fourier spectrum. So, in this we will be discussing the corner, cutoff and predominant frequency of the system using the Fourier amplitude spectrum plot. Okay. So, with this we will close today class. So, next class we will be discussing the corner, cutoff frequency and Fourier amplitude spectrum, how it varies for the different component of the data, how this will be useful for the other applications in the engineering seismology. So, thank you very much for watching this video. So, we will see you in the next class. Thank you.